Module 4, Lecture A, DC Circuit Analysis. By the end of this lecture, you will be able to compute equivalent resistance for series and parallel resistor networks using Python functions, calculate node voltages, branch currents, and power dissipation in simple DC circuits, and evaluate whether calculated circuit values meet component ratings and design requirements. Resistance networks, series resistance. In a series resistance network, resistors are connected end-to-end, giving current only one path to follow. Because every charge must pass through each resistor in order, the same current flows through all of them. The resistors' effects add together, so they can be replaced by one equivalent resistance to make circuit analysis or design simpler. In a series circuit, the total resistance is found by adding each resistor value directly. In Python, this can be handled with a simple function that takes a list of resistor values and returns their sum. This matches real circuits, where every added resistor increases the overall opposition to current, and it is easy to check against manual calculations. Series resistance is simple, but it builds important habits for accurate circuit work. Always keep resistance values in consistent units, such as ohms or kiloohms, and use a Python function to make inputs clear. In practical circuits, adding resistance can reduce power use in battery devices, but it can also limit the current available to components. Understanding these trade-offs makes resistance calculations useful beyond the numbers. Python code, series resistance. Use simple Python functions to calculate total resistance in a series circuit, making sure all resistor values use the same unit. The example also shows how to check whether the circuit meets a design requirement. The series resistance function calculates the total resistance of resistors connected in series, using a list of resistor values. It first checks that the list is not empty, and if no values are provided, it raises an error to show that at least one resistor value is required. This input check helps ensure the function only runs with valid data. The function checks each resistance value before using it. If any value is negative, it stops and raises an error, because resistance cannot be negative. This validation ensures only non-negative values are processed. The code finds the equivalent resistance of resistors in series by adding all the resistance values in the list. It then returns this total, so the program can use it elsewhere. Define three series resistor values, 220, 330, and 470 ohms. Set the supply voltage to 9 volts, which will be used to calculate the circuit current and the power dissipated by each resistor. To analyze a series circuit, first find the total resistance by adding all resistor values. Then use Ohm's law to find the current, by dividing the supply voltage by that total resistance. These two values describe the circuit's basic behavior under the given conditions. Create an empty list to store the power dissipated by each resistor. Then process each resistance value one at a time. For each resistor, calculate power as the circuit current squared multiplied by the resistance, following the electrical power law. Each result is added to the list, so the power for every resistor is stored individually. The circuit sets a maximum current of 20 milliamps and checks whether the actual current stays within that limit. The result is a true or false design check, showing whether the circuit meets the current requirement. The output first verifies the resistor values and the total equivalent resistance for the series circuit. It then reports the circuit current in milliamps for easier reading, shows the power dissipated by each resistor with appropriate rounding, and confirms whether the current stays within the required design limit. The script analyzes a simple series resistor circuit. It adds three non-negative resistor values, 220, 330, and 470 ohms, to find the equivalent resistance, then uses a 9-volt supply to calculate the circuit current. It also finds the power dissipated by each resistor using current squared times resistance, and checks whether the current stays within a 20 milliamp limit. The output summarizes the resistors, total resistance, current, power values, and whether the current requirement is satisfied. Parallel resistance. In a parallel circuit, resistors share the same voltage while the total current divides among different paths. Adding another parallel branch gives current more ways to flow, so the equivalent resistance becomes lower than the smallest individual resistor. When calculating this in Python, think in terms of how each branch increases total conductance, rather than adding resistances directly as in a series circuit. Parallel resistance means multiple current paths share the same voltage, so total current can flow more easily than through a single path. Lower resistance branches carry more current, much like wider openings allow more movement. A Python function for this should combine each branch's effect into one equivalent resistance, helping predict the total load in circuits such as battery-powered devices. Parallel resistor networks must be evaluated differently from series networks, especially in edge cases. A very low resistance branch can dominate the circuit and may create dangerous current if it is effectively a short, while a very high resistance branch may have little effect. A reliable computational method should handle these cases in a physically meaningful way. As a quick check, the equivalent resistance of a parallel network should always be lower than the smallest branch resistance. Python code, parallel resistance. In a parallel circuit, each branch has the same voltage across its resistors. To find the equivalent resistance, add the conductance values first, then convert back to resistance. A short circuit creates a path with very low resistance. The function first checks whether any resistors were provided. If the list is empty, it raises an error to require at least one resistor and prevents calculations on invalid input. The code checks each resistance value to make sure it is positive. If any value is 0 or negative, it raises an error. This validation prevents physically invalid resistances from being used in later calculations. For resistors in parallel, total conductance is found by adding the reciprocal of each resistance. Since conductance is the inverse of resistance, the equivalent resistance is then the reciprocal of that total conductance. This gives the overall resistance of the parallel circuit. A small parallel resistor network is set up with resistances of 100, 220, and 470 ohms, along with a 12-volt supply for later current and power calculations. The smallest resistance is then found using the minimum function to help describe the range of values in the network. First, find the equivalent resistance of the parallel branches using a function that combines their resistor values into one overall resistance. Then divide the supply voltage by this equivalent resistance to get the total circuit current. Finally, find each branch current by dividing the same supply voltage by that branch's resistance, showing how the total current is shared across the parallel network. Power in each branch is found by multiplying the supply voltage by the current in that branch. Each result is compared with a maximum safe rating of 0.5 watts. A branch is considered safe when its power is less than or equal to this limit. The output summarizes a parallel resistor network by showing the branch resistances, the equivalent resistance, and the smallest branch resistance. It then reports the source current, each branch current, and the power dissipated in each branch using appropriate decimal formatting. Finally, it checks whether every branch stays within the specified power rating and prints the resulting true or false value. This script analyzes resistors in parallel using valid positive resistance values. It calculates the equivalent resistance from the combined conductance, then uses a 12-volt supply to find total current, branch currents, and power in each branch. It reports these values, identifies the smallest branch resistance, and checks whether every branch stays within the half-watt safety limit. Mixed networks. Mixed resistance networks combine series and parallel sections, so they must be simplified in a structured way. The key is to identify parts that are clearly in series or parallel, reduce those sections, and repeat until one equivalent resistance remains. Python functions can support this process by calculating each simplified section and using the result in the next step. To analyze a mixed resistor network, simplify the closest resistor groups first, and then work outward. Combine end-to-end resistors as series groups and resistors sharing the same connection points as parallel groups. Each simplification can reveal new series or parallel relationships. Python can support this by using functions for series and parallel calculations, passing each result into the next step while preserving the circuit's overall behavior. In circuit analysis, how components are connected matters as much as their values. The same resistors can produce different equivalent resistances if arranged differently, which affects current draw, battery life, and lab results. Careful analysis, supported by Python functions, helps simplify and check circuits step by step so the final resistance value is reasonable. Python code. Mixed networks. Mixed resistor networks can be understood by reducing simpler groups step by step. Python functions can model this same simplification process, while rating checks help connect the calculations to practical circuit design. The function first turns the resistor values input into a list, so it can be handled consistently. It then checks that at least one value was provided, and if the list is empty, it raises an error asking the user to supply a resistor value. The code first verifies that every resistor value is positive, so only valid resistance values are used. It then finds the total resistance by adding the individual values together, which is the correct method for resistors connected in series. The function calculates the resistance of resistors in parallel by first turning the provided resistor values into a list, making them easy to process. It then checks that at least one resistor value is given, which helps avoid errors from an empty input. The code first confirms that every resistor value is greater than 0, which avoids invalid inputs and division by 0. It then adds the conductance of each resistor, where conductance is the inverse of resistance. Taking the inverse of that total conductance gives the equivalent resistance for the parallel network. 3 resistor values are defined for later circuit analysis. The first is 220 ohms, the second is 330 ohms, and the third is 470 ohms. These values will be used to calculate equivalent resistance and study how the circuit behaves. First, the 2 parallel resistors are combined into one equivalent resistance using the parallel resistance function. That result is then added in series with the remaining resistor to find the circuit's total resistance. The source voltage is set to 12 volts for later current and power calculations. Use Ohm's law to find the circuit's total current by dividing the source voltage by the total resistance. Then calculate the power in the series resistor by multiplying its resistance by the square of the total current. Finally, find the voltage across the parallel resistors by subtracting the series resistor's voltage drop from the source voltage. To analyze the parallel branches, divide the shared parallel voltage by each resistor's resistance to find the current through resistor 2 and resistor 3. Then find the power dissipated by each resistor by multiplying that same voltage by the current in its branch. These calculations show how much current and energy each component handles, helping confirm that both resistors operate safely. A quarter-watt power rating is used as the safety limit for each resistor. The power dissipated by the series resistor and the two parallel resistors is checked against this limit. If every resistor stays below the rating, the circuit is considered safely within its power limits. The output summarizes the circuit analysis by reporting the parallel resistance, the total equivalent resistance, and the source current in milliamps. It also shows the voltage across the parallel resistors, the current in each branch, and the power dissipated by each resistor using clear rounded values. Finally, it checks whether every resistor stays below the specified power rating and prints the result as true or false. This script analyzes a mixed resistor circuit with both series and parallel parts. It simplifies the parallel resistors, adds the series resistor to find total resistance, then uses a 12-volt source to calculate total current. It also finds the voltage across the parallel section, the branch currents, and each resistor's power dissipation. The output summarizes these values and checks that all resistors stay below the quarter-watt power limit. DC operating points. Node voltages. Node voltage helps describe a circuit's DC operating point. A node is a connection point where all points on the same conductor have the same voltage. To analyze a circuit, choose a reference node, usually ground, and measure all other node voltages relative to it. In battery-powered circuits, the negative terminal often serves as the reference, while the positive terminal is at the battery voltage. In DC circuit analysis, node voltages show the voltage each component experiences across its terminals. This voltage difference determines behavior, such as the current through a resistor. In circuits with several branches, knowing node voltages helps engineers check input states, sensor signal levels, and whether devices have enough supply voltage to operate correctly. When calculating node voltages, remember that the reference node and the circuit model are assumptions. Textbook problems often use ideal wires and perfect voltage sources, but real circuits can have wire resistance and large current changes that shift voltages. For example, a starting motor may briefly lower the supply voltage and affect nearby components. Understanding node voltages helps predict current flow and design more reliable systems. Python code node voltages. Use the voltage divider to calculate each node voltage, then compare those voltages to ground. Once the node voltages are known, use them to determine the current. The circuit's supply voltage is set to 12 volts of direct current. This value provides the reference for analyzing the voltages and currents in the rest of the circuit, including its resistors and nodes. The circuit has two resistors in series, a top resistor of 1,000 ohms and a bottom resistor of 2,000 ohms. These values are used to find the total resistance and determine how the voltage is divided between them. In a series circuit, the total resistance is found by adding the resistances of the top and bottom resistors. This combined resistance shows how much opposition the current faces as it passes through both resistors, and it helps determine the circuit's current and voltage distribution. In a series circuit, the current is found by dividing the supply voltage by the total resistance. This same current flows through every resistor, and it can then be used to find node voltages and the power dissipated in each resistor. Set the ground node to 0 volts as the circuit reference, and assign 12 volts to the node connected to the power supply. The middle node voltage is then found from the voltage drop across the bottom resistor, calculated by multiplying the branch current by that resistor's resistance. This gives the middle node's voltage relative to ground. Find each resistor's voltage drop by taking the difference between the voltages at its two ends. For the top resistor, subtract the middle node voltage from the supply voltage. For the bottom resistor, subtract the ground voltage from the middle node voltage. These differences show how the supply voltage is divided across the resistors. To find the power dissipated in each resistor, square the branch current and multiply that value by the resistance of each resistor. This uses the power relationship, current squared times resistance, applied separately to the top and bottom resistors. The resistor power rating is set to 0.25 watts, which is the safe dissipation limit. The calculated power for both the top and bottom resistors is compared with this limit to determine whether each one is operating safely. These checks help confirm that neither resistor exceeds its rated power and risks damage. The output summarizes a series resistor circuit by reporting the supply, middle, and ground node voltages, then the branch current through both resistors. It also shows the voltage drop across each resistor and the power each one dissipates. Power is converted to milliwatts and checked against a preset safe rating, giving a quick overview of the circuit's operating conditions. The script analyzes a 12-volt voltage divider made from 1,000 ohm and 2,000 ohm resistors in series. With 3,000 ohms total resistance, the circuit current is 4 milliamps, giving 4 volts across the top resistor and 8 volts across the bottom resistor. The resistors dissipate 16 and 32 milliwatts, which is safely below a quarter-watt rating. Branch currents. Branch current is the flow of electric charge through a specific path in a circuit and helps describe its direct current behavior. Once node voltages are known, currents can be found from the voltage differences across components and their resistance. The chosen current direction is only a reference. A positive value matches that direction, while a negative value means the current flows the opposite way. In direct current circuits, branch currents show how node voltages affect real components. Parallel branches have the same voltage across them, but lower resistance draws more current and higher resistance draws less. In series circuits, the same current flows through every component, even though each voltage drop may differ. This distinction explains why appliances on household panels draw current independently, while series decorative lights share one current path. Accurate branch current calculations help keep circuits safe, reliable, and within design limits. Since each component has a maximum current rating, too much current can cause overheating, damage, or incorrect operation. Branch current values also help engineers detect faults such as short circuits, choose suitable components, and confirm that current remains balanced at connection points. Python code. Branch currents. Find each branch current from the voltage difference between its connected nodes, using the chosen reference direction to set the sign. A positive value means the current flows in that reference direction. Then compare the calculated currents with the component's current ratings to check whether they are within safe limits. A node voltage dictionary records each circuit node's voltage relative to ground. In this setup, The input node is 12 volts, an intermediate node is 5 volts, and ground is 0 volts. These values provide a common reference for finding voltage differences, which helps analyze current flow in the circuit. A list of circuit branches stores the key details for each branch, including its name, start and end nodes, resistance, and current limit. This structure makes it easy to process each branch, calculate its current, and check whether it exceeds the allowed limit. This function finds the current through a circuit branch using the starting voltage, ending voltage, and branch resistance. It calculates the voltage difference by subtracting the ending voltage from the starting voltage, then divides by the resistance. This applies Ohm's law, where current is voltage divided by resistance. We first print a table header to make the circuit results easy to read. It labels each branch by name, current in milliamps, power in milliwatts, and status, so learners can quickly compare branch performance. The process checks each electrical branch by reading its key details, including its nodes, resistance, and current limit. It calculates the branch current from the voltage difference between the nodes divided by the resistance, then finds the power dissipated from the current and resistance. Finally, it compares the current's absolute value with the allowed limit and marks the branch as either operating safely or over the limit. The code prints one formatted summary line for each circuit branch. It shows the branch name, current in milliamps, power in milliwatts, and whether the branch is within its current limit or over it. This makes it easy to quickly check each branch's performance and safety. To check current balance at node N1, compare the current entering from VIN through the 700 ohm resistor with the currents leading to ground. The outgoing currents flow through R2 with 1000 ohms of resistance and through the LED path with 2500 ohms. This shows how current is distributed around node N1. To check current balance at node N1, compare the incoming current with the total outgoing current. The resulting mismatch shows whether the node voltage may need adjustment, and reporting it in milliamps makes any imbalance easy to see. The script evaluates circuit branch currents from node voltage differences and resistance values. For each branch, it finds the current, calculates the power dissipated, and checks whether the current stays within its limit. It then reports each branch's current, power, and status. Finally, it compares inflow and outflow at node N1 to show any current imbalance, which may indicate that the node voltage needs adjustment. Power dissipation. Power dissipation describes how electrical energy is converted as current passes through a component. In direct current circuits, resistors often turn energy into heat, while other devices may produce light, motion, or sound. By knowing the voltage and current, we can understand how energy is transferred in real circuits, such as a lamp glowing and warming, or a resistor releasing excess energy as heat while controlling current for an LED. Power dissipation is important in direct current circuit analysis because it shows how much electrical energy a component turns into heat. Even if voltage and current values seem correct, a resistor or other component can overheat if it dissipates too much power. Checking power helps identify wasted energy, reduced battery life, and possible component damage in both low-power and high-power circuits. Power dissipation helps confirm that energy is balanced in a circuit. Sources supply power, and loads absorb it. Resistors and lamps typically absorb energy, while batteries provide it, depending on current direction and voltage polarity. Checking power dissipation is especially important in circuits with multiple sources, because it supports safe, efficient design choices for components and layout. Python code, power dissipation. Calculate the power each resistor dissipates at its operating point. Then compare that value with the resistor's power rating. This helps confirm the component can handle the expected load safely. This means the script does not need any extra Python packages to run. It uses only built-in Python features, so it can run without installing external libraries. The resistor power function calculates how much power a resistor dissipates. It takes voltage and current as inputs, multiplies them, and returns the power in watts. A resistor data list is created to store key details for each resistor. Each entry includes the resistor's name, voltage, current, and power rating, making the data easy to access for later calculations and comparisons. The code prints a header that labels each output column, including the resistor name, calculated power, power rating, and safety status. This makes the results easier to read and compare. The process checks each resistor by using its voltage and current to calculate power in watts. It then compares that power with the resistor's rating to decide whether the resistor is within limits or too hot. The results are displayed in a neatly aligned table showing the resistor name, calculated power, rating, and status. To find the total power absorbed by the resistors, add the power calculated for each one. For each resistor, use its voltage and current with the resistor power function, which multiplies them to get power in watts. The sum then gives the combined power for all resistors. Calculate the source power by multiplying 12 volts by 0.026 amps. Then compare this delivered power with the total power absorbed by the resistors. If the two values match, it confirms that the circuit calculations are consistent. The script checks whether each resistor is operating within its power rating. It calculates power from voltage times current, compares each result with the resistor's limit, and reports whether it is safe or overheating. It also adds the total power absorbed by the resistors and compares it with the power supplied by a 12-volt source at 0.026 amps, giving a concise overview of both component status and overall power balance. Design verification. Rating checks. Rating checks confirm that a circuit's calculated voltages, currents, and power levels stay within component limits and design requirements. After analyzing a DC circuit, each value must be compared with safe operating ratings such as maximum voltage, current, and power. This helps prevent failures like overheating, switch damage, or diode breakdown, and ensures the circuit is safe and reliable in its intended conditions. A rating check confirms that each part of a circuit stays within safe limits, even if the circuit appears to work. Check resistor power dissipation, trace current, capacitor voltage, and the combined voltage, current, and power limits of transistors or regulators. This matters because a working output can still hide an overstressed part, such as an overheating resistor or a signal that could damage a microcontroller input. Rating checks must account for the difference between ideal calculations and real operating conditions. Actual circuits can face changes in supply voltage, component tolerances, temperature, and startup currents that may create higher stress than steady-state analysis suggests. Checking these worst-case conditions helps determine whether components are properly rated, need upgrading, and can operate safely and reliably. Python code, rating checks. After completing circuit calculations, check that each component's rating is adequate. Compare the computed stress on the design with safe operating limits, then report a concise pass or fail result. We begin by defining the circuit's basic values: a 12-volt supply, a 470 ohm resistor, and a resistor power rating of 0.25 watts. These assumptions set the voltage source, the resistance in the circuit, and the maximum safe power the resistor can handle. Set the switch current rating to 0.05 amperes, the LED forward voltage to 2 volts, and the LED operating current to 0.02 amperes. These key values ensure the switch and LED operate safely and properly within the circuit. To analyze the LED resistor branch, first find the voltage across the resistor by subtracting the LED forward voltage from the supply voltage. Then divide that resistor voltage by the resistance to get the branch current. Finally, use the current and resistance to find the resistor's power dissipation so you can confirm it stays within its rated limit. The check limit function verifies whether a measured value stays within an allowed limit. It compares the value to the limit, marks the result as pass if it is within range, and fail if it exceeds the limit, then returns a formatted summary showing the item name, value, limit, unit, and status. The code checks whether the circuit's branch current meets or exceeds the required current. If it does, the current status is marked as passing. If not, it is marked as failing. This provides a quick way to confirm whether the circuit satisfies its current specification. The code runs design verification checks for a DC indicator circuit. It prints a header, then reports whether the resistor power, switch current, and LED current meet their required safety or performance limits. The final decision checks whether the circuit design meets its key limits. The resistor stays within its power rating, the switch can handle the branch current, and the required current is achieved. If every check passes, the design is accepted. If any check fails, the result is to change the components. This script checks whether a simple direct current indicator circuit is safe and functional. It calculates the resistor current and power, then verifies that the resistor, switch, and LED are all operating within their required ratings. Each check is reported as pass or fail, followed by an overall decision on whether the design is acceptable or needs component changes. Component rating checks. Component rating checks verify that a circuit's calculated voltages, currents, and power dissipation stay within the safe limits of the real parts. Even if a resistor or diode appears to work electrically, it can fail if it exceeds its power or current rating. The purpose is to ensure every component can perform its role safely and reliably in the final design. To check component ratings, identify what stresses each part and compare the worst-case conditions with its datasheet limits. Resistors are mainly limited by power and heat, capacitors by maximum voltage, and semiconductors by ratings such as supply voltage, current, and power dissipation. These checks help ensure parts remain safe under real operating conditions, including startup currents and heat buildup, not just ideal conditions. Component rating checks make sure a circuit will remain safe and reliable under real-world conditions, not just ideal calculations. Variations in supply voltage, manufacturing, temperature, wear, and heat buildup can make a chosen part unsafe or unreliable. Designers may need higher-rated components, adjusted values, or better cooling so the final circuit is durable for its intended use. Python code. Component rating checks. Use calculated circuit values to check that each component is properly rated. Then compare the expected operating conditions with safe D-rated limits. This example applies that process to a simple LED circuit. The circuit uses a 12-volt supply with an LED that drops 2 volts while operating. A 470 ohm series resistor limits the current through the LED. helping it run safely within its rated limits. The resistor is rated for 0.25 watts, and the LED is rated for 0.02 amps, marking the maximum safe limits for each component. A safety factor of 0.8 is applied to lower these limits, adding a margin of protection for reliable operation. To size the resistor in an LED circuit, first find the voltage it must drop by subtracting the LED forward voltage from the supply voltage. Then divide that resistor voltage by the series resistance to get the branch current. Finally, determine the resistor's power dissipation by multiplying the square of the current by the resistance, so the resistor can be rated safely. Safe operating limits are found by applying a safety factor to each component's rating. The resistor's safe power limit and the LED's safe current limit are both reduced from their maximum ratings to help prevent overheating or failure. This keeps the circuit operating within conservative, reliable limits. The code checks whether the resistor and LED are operating within safe limits. It compares the resistor's power to its safe rating and the LED's current to its safe rating. The circuit design is considered acceptable only if both checks pass. The safety check labels each part as pass or fail based on its limits. The resistor passes if its power use is safe, and the LED passes if its current is safe. The overall design passes only when both components pass. Otherwise, the design fails. The output reports the key safety checks for the circuit. It shows the LED branch current in milliamps, the resistor's actual power dissipation in watts, and the resistor's safe power limit for comparison. It also shows the LED's safe current limit in milliamps, making it easy to compare against the actual current. The output reports whether the resistor power and LED current are within safe limits, then gives an overall design status. If any check fails, the design should use higher rated components or adjust the resistance to keep the circuit safe and functional. This script checks whether a simple LED circuit operates safely by comparing calculated LED current and resistor power against derated limits. Using a 12-volt supply, a 2-volt LED, and a 470-ohm resistor, it applies an 80% safety factor to the resistor's quarter-watt rating and the LED's 20 milliamp rating. It then reports the calculated values, marks the resistor and LED as pass or fail, and gives an overall design result with a warning if adjustments are needed. Design margin check. A design margin check verifies that a circuit will be safe and reliable in real conditions, not just correct in theory. After calculating voltage, current, and power dissipation, you compare them with component limits and required performance. The circuit should stay below maximum ratings, so it can tolerate changes such as temperature shifts and supply variation. This buffer, called design margin, helps keep the design robust beyond the simplified model. In a DC circuit, design margin means choosing components that operate safely below their maximum ratings. Resistors need enough power capacity to avoid overheating, and capacitors need voltage ratings above expected levels to handle startup or transient changes. These checks are especially important in battery-powered and automotive systems, where voltage can vary, and they help ensure the real circuit remains reliable. Design margin helps ensure a circuit still works when real components vary from their ideal values. Since resistor tolerances can shift thresholds, currents, or control voltages, a margin check tests whether the circuit remains safe under unfavorable changes. If the design is too close to its limits, the solution may be to adjust component ratings or improve thermal management. Python code. Design margin check. Design margins help protect real circuit components by keeping calculated values below their ratings. This example focuses on checking a resistor divider for safe operation. The circuit uses a 12-volt source feeding a voltage divider with a 1,000-ohm top resistor and a 2,000-ohm bottom resistor. These values are used to find the voltage at the node between the resistors and the current through the divider. The component limits are set to a power rating of 0.25 watts and a voltage rating of 16 volts. A minimum safety margin of 50% is also required, keeping normal operation well below these limits to protect against unexpected variations. To analyze the voltage divider, first add the top and bottom resistor values to get the total resistance. Then find the current by dividing the source voltage by that total resistance. Finally, multiply the current by the bottom resistor value to determine the voltage at the node between the resistors, showing how the source voltage is divided. Calculate each resistor's power dissipation by multiplying the square of the divider current by that resistor's resistance. Compare the top and bottom resistor power values and use the larger one as the worst-case dissipation. This identifies which resistor has the highest power demand and is under the most stress. The margin percent function shows how much a component's rating exceeds its operating value. It takes the rating and operating value, compares them, and returns the difference as a percentage. This margin helps assess whether the design has enough safety buffer. The code calculates power and voltage margin percentages using a margin calculation function. It compares the power rating with worst-case power dissipation and the voltage rating with the source voltage to show how much each rating exceeds the expected demand. Finally, it checks whether the power margin meets the minimum required design margin. The code checks whether the voltage margin meets the minimum requirement, then combines that result with the power margin check. If both margins are adequate, the design passes. If either one is insufficient, it needs revision. This final status shows whether the design margins are acceptable. The code reports key circuit design results in a readable format: node voltage in volts, divider current in milliamps, and worst-case resistor power in milliwatts. It then shows the power and voltage margins as percentages to indicate how far the design is below its rated limits. Finally, it prints an overall pass or revise status to summarize whether the design meets the required safety margins. This script checks the design margins of a resistor divider by calculating the divider current, node voltage, and power dissipated in each resistor. It identifies the worst-case power dissipation, then compares the power and voltage margins against a required minimum of 50%. The output reports the key values and gives a pass or revise result depending on whether both margins are sufficient. In this lecture, you learn to compute equivalent resistance for series and parallel resistor networks using Python functions, calculate node voltages, branch currents, and power dissipation in simple DC circuits, and evaluate whether calculated circuit values meet component ratings and design requirements. In the next lecture, Lecture B, we will go over AC and frequency.
Thank you for your attention. See you all in the next lecture.